Today, we're really fortunate to have Dr. Mark
Besonen.
Yes.
It's Finnish. Not too many Finnish here in South Texas, you know. So
he is a associate research scientist at the Hart Institute, Texas A&M, Corpus Christi. He has degrees, a BS from Tufts, a MA from the University of Minnesota, and a PhD from the University of Massachusetts. So a lot of knowledge there, and we're very lucky to have him. He's going to tell us about geologic changes in the bay, the barrier islands, and I hope what we might be able to expect in the future. So I'm going to turn it over to you.
thank you for the invitation to come here, and it's a pleasure for me. Thank you for coming in on Father's Day. I'm a father as well, but my family's traveling, so it works out well. So I was free for the afternoon. Anyway, so I'm going to tell you a little bit about Texas coastal change, but it's from a geologic perspective. Everybody lives it being on the coast, right? But we take a different perspective as geologists. And it was mentioned that I was an undergrad at Tufts. I did geology there, but I didn't do just geology. I also did classical archaeology. And I studied Greco-Roman archaeology. And I didn't know when I got in there that what I was going to do. My parents said, go to school, find something you like. And I'm like, okay. And so I tried geology and I tried archaeology in my second semester. And I said, wow, these things go together great because they're both looking at sort of stratified contexts. I know this is not history, it's archaeology, but one is looking at natural stratified layers, geology. The other one was looking at stratified layers from humans, you know, whether it be artifacts or architectural fragments, you know, bones, whatever. So I realized these things go together very well. And then for my master's thesis, I went on to University of Minnesota in Duluth to work with this guy named Rip Rapp. He called himself the father of geoarchaeology. And so he had worked all around the Mediterranean. And for my master's thesis, I was able to work in a river valley in Greece, putting together a coastal landscape. But so I had to make a choice at one point to become more geology or more archaeology. There was more opportunities towards that geology side. So that's why I went there. But I was fascinated with history and such and archaeology. So when we think of coastal change, it occurs at a variety of different scales. And I'm talking about time scales and physics scales. And one of the neat things about this is, you know, if you were to live in the mountains are beautiful and such, right? But if you were to live out there, you look at it at the end of your lifetime and nothing has changed. You could look at it at the end of 5 or 10 lifetimes and nothing as much has changed. But the coast is very different. It's very dynamic. It changes on all different time scales. And so as a scientist who studies the surface of the earth, it's really fascinating to be looking at that because, you know, you can actually see something happening on your lifetime. And so I just have a simple plot here and on this axis, the horizontal axis, talks about size. So it's about spatial size. So I go from sand grains to beaches, to islands, to coastlines, to continents. And on this axis here, I go on a time scale from days to years to decades, centuries, millennia. And so in general, there's a pretty good relationship between these factors. For example, when we're dealing with something small, like sand grains or beaches, we can see changes on the order of days and years, right? That's normal. When we can take it a little bit bigger when we're dealing with something like islands. Those have generally a longer time span that we can see changes on before we can actually see changes, right? If you go every day, you're not going to see it. It's basically you're zooming out. So years to decades to centuries. And we go on a bigger scale when we look at huge features like deltas or coastlines. This is the Mississippi Delta, right? Those, to see changes of them, there are some changes on the small scale, local scale that happen rapidly, but in general, big scale changes, we're talking about the order of millennia. And so in general, I mean, there's this relationship between the size of the feature that you're thinking about, the Earth's surface feature that you're thinking about versus how easily you can see the change. There's some exceptions though, right? And you guys all know that very well for living here through Hari, for sure. Once in a while, we can start to see sort of a large scale change over space on the order of islands and coastlines just related to a single event like a hurricane. So anyway, we as a geoscientist studying the coast, we're trying to understand all these different time and spatial scales stuck together. And it turns out that there's different tools that you have to use to study each of those, because one set of tools doesn't work for all of them. One of the things that we do is we use basic field observations. We can go out there, right? And we can take a look at the vegetation, we can make small trenches, we can survey in the elevation of dunes and such. That's something that we do in modern days, right? And that tells us about what modern processes are happening. Perfect, that's what we need to kind of ground everything. But the problem about that is, not a problem, but the limitation of that is that you have to be physically in the field, you know, and a body can't be in 10 different spots at once. If we're looking at the whole coast, we need to have some type of larger scale way to understand what's happening along the coast. And so this is also only good if you're dealing with things that are happening right now or moving forward in time, right? How do we go back? How do we get that historical perspective? Because in geology and many of the sciences, we have this expression that we say that the present is the key to the past, but the past is also sort of a key or a guideline to what we can expect in the future. So we really need that past perspective to understand kind of where we are, what a baseline in the system is. So where I work in the laboratory, we deal with a lot of remote sensing, and we use things like satellite imagery and aerial imagery. Satellite imagery is great, but it's only been available since the 70s, right? It gives you a big picture view, and back then it wasn't the best. It got progressively better. And the thing is, it just doesn't normally have as much detail as something like field observations or even something like aerial photography that I'll talk about in a minute. So this is good for recent time, you know, the last couple of decades, and also gives us this really big picture view. And we can do a lot of things with satellite imagery because we don't have just visible light that's coming back, like a visible image. We can look at different wavelengths, different spectrums, so we can, we don't have to go into a lot of details, but you can get a lot more information than just like what you would see with your camera. So, but that's why looking at the different electromagnetic spectrums that these satellites are documenting. And if we go to aerial imagery and data collection, and I say imagery here, I'm showing you just things that you can see with your eyes, but there's also a lot of things that we can collect from small airplanes, right, flying over the coast. Tremendous amount of detail, right? There's a tremendous amount of detail in this type of stuff. We can see down to individual plants and types of vegetation. So that saves us time from going in the field, right? So we can do like a big survey all at once. The problem about that is that only goes back to maybe, well, very commonly to the 50s, 40s, there's some in the 30s, maybe some in the 20s. So that doesn't get a long-term perspective either. And the other thing about this type of stuff, this type of imagery that's captured by a small airplane or data, that happens once in a while. It happens maybe like once a year. Like in the last decade, we might have it once a year, once every 2 years. As you go back in time, it's less and less. You might have it once every 5 years, once every 10 or 15 years. And so that doesn't give you, you know, all the information that you need. You want the most complete story possible. So anyway, that's a trade-off between these types of things, between aerial imagery and satellite imagery, because one of the cool things about these satellites is they are flying overhead every single day. There are some satellites that cover the cover the planet, come back for return intervals every 5 days. So you can basically take a look at what those satellites are seeing and watch the coast change every 5 days with a lot more information than is just visible light. So those are some of the tools that we use to help expand instead of just going out into the field, because we can only hit so many spots at once. Here's something great and probably near and dear to your hearts, are historical maps and documents. And right now I'm going to show you just the maps, but I have to tell you something about documents in a couple slides down. That's kind of related to my master's thesis. But here's a beautiful example. This is a map that's from 1860 or so, and it was put together by the U.S. Coast Survey. This U.S. Coast Survey was something that was started up by Thomas Jefferson, or he was the guy that kind of put it into gear. In the early 1800s, of course, at that point, we were interested in trying to figure out what we had, you know, in the U.S. here. We had this huge territory. We didn't really know what was there. So he had all these missions out to document stuff. They didn't really get going until, for various reasons, like the War of 1812, they didn't really get going until about 1820, 1830, like that. And then they started sort of these systematic surveys, starting up towards the East Coast, coming down, looking at every bay, estuary, things like that. And I'm from the Boston area, and so there's just incredible stuff you can read from the 1850s or whatever, from the harbor commissioners up there, from these survey, the survey plans that they had. Anyway, these things are fantastic because it wasn't just some map that they drew willy-nilly about, you know, go to the 3 rocks over there, take a right, go 100 meters and do this, right? Those guys, they had gone to Britain to collect gear like transits and, you know, rods and things like that. It was really well documented, and they meticulously plotted out the coastline. I mean, they basically covered the whole U.S. coast, which is incredible. And so these are kind of like the gold standard if we get to that age, like from 1850 or so, or in the mid 1800s, because these things are really well documented. And we can basically draw a shoreline on these things. We can trace it along here, and then we can overlay it on modern imagery, and we're like, wow, it's pretty good. We can actually see what changed. And with respect to San Jose Island, we could see a couple areas where there's been more erosion than others. So there's also a lot of detail in these things. If you look, you can't see it on this TV and from where you are, but you go in there, you can see different types of environments. There's marsh, there's sands, you know, from the dunes and stuff. So it gives just a tremendous amount of information. So anyway, this unit is still operating, this coast survey. It's part of NOAA nowadays, but it's got its roots back into the early 1800s. Anyway, so there's a variety of historical maps, and actually I've seen that you guys had some historical maps on the website, at least, just a couple of pictures. So I would like that one day to, you know, explore the possibility of looking at those with you guys, because while this is kind of a gold standard, there could be a lot more information as well, because these are only available for certain periods of time. So how good is that gold standard? I mean, it's fantastic. And so this is an example of something that we would do just to understand how we deal with those old U.S. Coast Survey stuff. This is a recent image, an air image, you know, from a little plane flying over Padre Island or South Padre Island. And what we did is we basically drew a line along the wet, dry sand line, as we call our shoreline, is the wet sand, the dry sand marking line, more or less. And we've called it Island Yellow. That's where it is. There's a map, there's one of those U.S. Coast Survey maps that's available for the same area. They're available for the whole coast. And it shows us what the system was like in 1867. And again, there's no question about those guys were accurate. Even if they're off a couple of meters, we're not talking about a big problem. This is what the system looked like in 1867. And if we stop and put those two together, we can get a lot of information about how the coast changed. The shoreline was out here in 1867, and the backside of the island was around here. In 2009, it was here and here. We're looking at about 1,500 feet of difference. The shoreline has retreated, gone backwards towards the land over that period of time. So it's a significant chunk. Now just stop and think for a moment, if that's kind of the rate of how things are moving, what about all the waterfront property that we have nowadays? Where's that going to be in 50, 100, 150 years? And that's, as we'll get to a little bit later, this is with kind of a slow, gentle sea level rise, because this is what barrier islands do. Barrier islands, as sea level is rising, they move back towards the land. Oh, by the way, if you have any questions or comments, you can stop me. If I say something, I'll probably talk in meters. I'll try to convert it to feet or whatever, miles. But if I say, you know, just stop me. I have no problem with that.
So just to orient us, the Queen Isabella Causeway is off to the right of the picture?
Excuse me?
The Queen Isabella Causeway
Yes,
is off to the
yes,
right.
yes. Yep. So those are what take us to like the last, you know, couple of decades, last 50 years, 100, 150 years. How do we go back further in time? Because we need kind of a long-term perspective to figure out what's happening. And so to take us further back in time, we use a bunch of different geological tools and techniques, things that we would use to study the Earth, but we're using them sort of in this hybrid fashion to study real recent Earth. And so I'm talking about things like sediment cores, and here's a picture of one of my classes taking a marsh core, boom, 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 banging it down into the marsh. And Here's kind of a picture of what would be there. This is the bottom of the core down here, so it's deepest. This is the top up here, you can see marsh grass. And what's really cool about this is you can go in there and look at those layers, layer by layer by layer by layer. As you move, as you go deeper and deeper and deeper, you get older and older and older. As you go upwards, you get younger and younger and younger. And so then we can slice and dice that, and we can study different materials in it, like pollen, diatoms, ostracods, other types of microfossils, plant remains, just the pure sedimentology. We can get an understanding for what a particular environment was like, and then how it changed through time. Like this by coincidence, is a core from Boston, a marsh in Boston Harbor. And we can see in this marsh grass, and then we can see a bunch of a bunch of sand layers that are probably related to hurricanes that washed into that marsh and carried sand into the marsh. And then the marsh resumed building, and then another storm came in and put another layer. And so we can use something like that to develop sort of a history, a long-term history of hurricanes, back beyond what we would use for just historical records. Historical records are really important, but this could take us even further, because if we're looking at periods of climate in the past that are going to be similar to climate systems where we're going, we have to go back a little bit further. So anyway, that's just one of the geologic techniques. We don't have to go into a lot of the details, but we use those geological tools to help us go back even further in time. And what's really important is it's a really important interface between those two. To make that gap, it's really historical and documentary evidence that helps us interpret something like this sediment core. If we didn't have historical records, and Boston's wonderful because we go back to basically 1640 there. If we didn't have long historical records, well, this only goes down to about 1900, but I have other sediment cores that go back further with sand layers and stuff that are related to much older hurricanes. So anyway, we use these tools to look at longer time frames. And here's kind of a flashback to the past, from my archaeology past, because as I mentioned, when I was a master's student with this gentleman, Rip Rapp, in the University of Minnesota, Duluth, because of all the connection, we worked out something with an archaeological project called the Nicopolis Project out in northwestern Greece, a zone called Epirus. And so this is the fascinating part. This is the fascinating part about historical documents, okay? Because in this area, maybe we have from European settlement, about 150 years. If we go back to the Spanish archives, there's a Archivo General de Indias in Seville, Spain, that can go back, several hundred years. It gets a lot of information. But otherwise, we have much less in the New World versus the Old World. And by Old World, I mean sort of Europe and the circum-Mediterranean region. And so here's the story with this. This is a river valley that the archaeologists were studying, and they read in Homer, back in the 8th century, from the 8th century BC, when it was written, that there was this city that was overlooking the sea. There was a city that was overlooking the sea, and this is the modern configuration. The only place that they could be overlooking the sea is up here, right? And so I was able to take sediment cores at different spots and show that the sea had one time been as far back as here, and just a couple thousand years ago. So about 4,000 years ago, it was back 5 to 6 kilometers. And in fact, there was this ruins of a city here. Nobody had a name for it. This was the city that Homer was talking about. That's documentary evidence from 3,000 years ago. So it's not quite the same level of like really good documentation that you get with those US survey maps, but it's just incredibly cool to think that there is even some literally historic evidence that goes back that far, and we can interface with it with geology as well. And this is pretty impressive, because what it shows is that this coastline has advanced or prograded about 3 miles over that period of time. I mean, it's nowhere near where people were thinking it would be. So I just showed you a Texas coastline that was moving backwards or receding or retreating. I'm showing you a shoreline in the Mediterranean now that's advancing. To be honest, there's every grade in between, and not just on those 2 different areas, even within Texas itself. So we don't have time for a full geology lesson, and I'm sure you'd kill me if I try to give it to you, but let me tell you that there's a couple of things that are sort of the primary controls about a shoreline, whether it's advancing or whether it's retreating or what's particularly happening to that coastal feature. One of them is the amount of sediment that's available. And you would never think it when you go to the beach, you come home and you have sand everywhere, right? But there's a limited supply of sand out there. You go 8 or 9 miles offshore, and then by that point you're into mud. And so there's a limited amount of sediment supply we have in this area, at least. If you don't have sediment, how can you build something forward? In fact, if you don't have sediment, usually things are going backwards because as you have erosion start cutting into the shoreline, and then you lose it. So anyway, sediment supply is a big consideration. Do we have enough sediment to actually build these coastal features, barrier islands or whatever? Another thing are the actual, the mechanisms that move that sediment around. We're talking about wind, waves, currents, storms, things like that. So that's another big factor there. And there's many local factors that depends on which way the shoreline is facing, the climate system, a whole bunch of things like that, the tidal range and such. Here's another really big control. Which is relative sea level. And that's a really important control, especially for all the barrier islands along the Texas coast. And it's a little bit, makes us a little bit nervous nowadays because sea level, we can see is starting, we'll talk a little bit more later about what sea level has been doing, but it's starting to rise, it's starting to pick up and accelerate, getting faster and faster and faster. And there's some problems with that because we'll take a look at when all these barrier islands formed and see what sea level was doing at that point. So anyway, so those are some of the big controls that we see on what actually helps a shoreline advance or retreat or just the type of feature that you would form there. As I mentioned, I showed you an advancing shoreline in the Mediterranean. I showed a retreating shoreline from Port Isabel. If you look along the Texas coast as a whole, there is a whole range, and I know you can't see it from where you are there, but you can just see there's a series of colors, reds to orange to yellows to greens and such. And so here's the coastal bend, we're going all the way up to Galveston and Sabine Pass. And these color codes, green show areas that have been advancing, that the shoreline has been moving forward at the expense of the ocean. And then the yellows and the oranges and the red tones show areas where the shoreline has been moving backwards towards the land. And so this is kind of a general trend since the 1930s. This is a whole suite of data put together by some folks at Jeff Payne and group at the Bureau of Economic Geology in Austin. So it's a tremendous amount of work to put together these records, but they give a good picture of what's happening sort of over that time frame since the 1930s. And if we take a look, we can see areas that are doing quite well in the sense, yellow is approximately neutral. Green means the shoreline is moving forward. Orange means you're moving backwards. You're losing shoreline. That's from 1930 to 2012. If we look at just 2000 to 2012, it's like we got this data set, and now we're just there's an earlier part of the data set when things were different, and now we're looking at the most recent part, the last 12 years, and we do that same type of analysis to see where the shoreline is staying the same, or whether the shoreline is moving forward, or whether the shoreline is being cut back. We can start to see that a lot of things have changed here. And in certain areas, like down by Packery Channel, over by the Aransas Pass and stuff like that, there are sort of hot spots where a lot of times we see colors that are green, like strongly advancing shoreline, and then we see right next to it a red. And so that overall system is changing. And a lot of these changes are things that we've done sort of by man-made structures in the past or in recent time. So what am I talking about in particular? You guys probably have heard of the concept of longshore transport. And so longshore transport is one of our mechanisms for moving sand along the coastline, out in the water. If you just go in the water and you float, you see yourself, and you look 20 minutes later, if you've been floating, you've actually moved down the beach, right? Because as the winds that blow up onto the shoreline, they're usually coming at an angle, and so they're pushing the water a little bit to one side, and that carries the sand a little bit to one side. Well, what are our winds here? Southeast down about 9 months out of the year. Strong southeast winds, they're coming up like this. And so they're also coming up here. And then we also have a component from the northeast as well during the winter, right? And so we have this net transport of sediment coming sort of from the Mississippi Delta area, traveling west along the shoreline, along the Texas and the coastal bend. And then we also have another source coming from the Rio Grande Delta, and they meet up here a little bit south of Baffin Bay in the area of the land cut. And so it's like these two zones are coming together. But in general, the thing is, up here, the sediments are moving from the north to the south, and from down a little bit lower, they're moving from the south up to the north. So, and so maybe you guys have heard of Big Shell Beach. Well, so that's about the convergence zone, the net convergence zone between these two areas. So anyway, that's sort of a generalized picture of how we're moving material here along the Texas coast. This is what happens when we interfere with that natural process. And this is up from Massachusetts area, but somebody decided, I'm going to put in a little groin, right? They put an obstacle in the flow of that sand traveling along the beach. And what happened is that sand accumulated on this side, and their neighbors downflow of it got I don't know, I can't say bad words, got gypped, right? They lost all their sand. And so that neighbor says, darn it, I'm going to put up my own groin. And before you know it, the whole coast is full of groins, right? So that's a little bit of a problem. This is exactly what happens when you put up a system like that perpendicular to the shoreline. You start to trap sand, and that makes sense geologically. You got sand moving along, and you need a certain velocity. The water has to be moving at a certain speed, and if all of a sudden you put an obstacle there to slow down the water, well, the water slows down and the sand falls out of suspension, and yeah, you got a nice beach, but your neighbor next door is losing all the sand that they were getting before. So a lot of those hot, cold areas that I showed you on the one from 2000 to 2012, those are areas where there is some type of obstruction there.
Did they assist what Galveston did with their beach?
Yeah, so this is, I'm not sure what particular beach you're talking about, but yes, probably, guaranteed this is what they did.
Seawall, they got all those structures.
And the problem is, it's almost like an endless cycle. As soon as you put in one, the next guy is really they're bad on their luck, so they put up one, and it's a perpetual process. The only way to undo it is to put a series of nested ones that are smaller and progressively smaller and progressively smaller. And some of them are closer together, yeah. So it is like an engineering feat to be able to do that. So, for example, and I tried to find older imagery for Aransas Pass. I couldn't find it, but it was very easy to find stuff for Packery Channel, right? Because that's brand new, or whatever, 15 years old. And so I've got a series of images, air images that are taken of the same spot. They're all what we call georeferenced and such, so that spot A on one image is exactly equivalent to spot A on the next image, maybe a meter or two or something different. But they're all exactly on top of each other, right? And so this is starting in 2004. As soon as they built it out, and this is the shore, I drew that wet dry line from 2004 right there, which is this thing. Can you see this dark light area? So that's what we consider our shoreline. Here's what happens in just in a couple of years. And so you can see what's happened by putting up that obstruction like that. They've trapped a lot of sand. Now the problem is what happens to the folks down the coast, because it's still going in that north to south transect there. That's very similar to what's happened up at the Aransas Pass jetties as well, right? That shoreline has been built up, which is great for those people, but it's probably, and we're talking about a large distance, but if the sand's stopping there, then it's not going someplace else. Let's put it that way. So anyway, that's always a consideration to think about when we're with these systems. When we put in some type of obstruction, we're going to really change the hydrodynamics and how we move along sediment. All right, I'm going to tell you now about an absolutely fundamental process for all of the Texas coast, because we've got the best, longest, biggest barrier island systems in the world, right? Sounds very Texan, doesn't it? I'm getting there. I'm a Yankee, but I'm getting there. So it's a process called barrier rollover. And this is what barrier islands do when sea level is rising or rising slowly. It is their only job in life, and this is to personify them. They're trying to, as sea level rises slowly, they try to migrate backwards towards the regular, to the continental, or to the shoreline there, to keep up with the sea level rise. And so I've got a couple of figures here to show you kind of a progression. And we start off with a beautiful dune system like you might see here on Mustang Island or whatever. And there's, in the back, so this is the ocean side, this is the bay side back here, and there's a beautiful marsh, some shrub forest in this particular picture. At time 2, okay, some point in the future, we have an initial breaching, some pass through the dunes there. And so we have an overwash event. We carry sediment from the front side of the system to the back side of the system, which anybody who lives on an island hates and stuff, but it's an absolutely fundamental process for helping that island keep up with sea level rise, because on the back side of the island, all there is this fine material from the bays and such. So you need to carry the sand from the front side of the island to the back side of the island. The breach is good if you want the island to survive. And so during this first period of time, basically we just cut back the dunes and we started to deposit sand in the back side of the island, right? So what's important, if to note here, see this marshy layer or this vegetation layer, it's right here. As we start to have these overwash events, they get covered with sand. So we keep that process going as sea level continuously rises slowly, and this overwash happens more and more frequently. And so we're looking at a difference. Maybe this is more like towards Matagorda or South Padre Island type configuration where there's a lot of overwash that's quite frequent. Whereas here we're looking at something like Mustang Island, where we've got a very nice dune system to help protect the area. But by this point, that dune line is pretty much gone. And if the system is given enough time to readjust, what it will do is it can reform a new dune line, right? But here's the difference. Now that dune line is X amount of distance inland, right? Because we've basically pushed the whole island back. We've forced it to roll over on itself. That vegetation that I talked about is now cropping up at the front on the beachfront. If you get a really low tide, you can sometimes see it out there. So the island rolls over itself like that. We call it rollover, and that is a fundamental process that the island or that the system has to follow to survive. All right. Here's what we look like nowadays. All right. This is pretty much the coastal bend going down from Baffin up to Matagorda here, and we've got a beautiful barrier island system in the front, and we've got a beautiful lagoon on the back. Has anybody ever noticed that between Flower Bluff, the Encinal Peninsula, and then the Live Oak Peninsula up here, this Rockport area, is another high area? And then right behind it's another low area. You've got all these secondary bays like Oso Bay and branches of Copano and such. Also, okay, keep that in mind, because this is what we're seeing at the present day. We're going to go into sea level a little bit more now because we absolutely have to understand this. It's fundamental for understanding what's happening at the coast here. But sea level is very much controlled by what's happening for global temperature. During periods of very cool climate, remember back to the water cycle in school, we evaporate water from the ocean, we bring it on land, it precipitate it down. if it's very cold, it can start to accumulate as snow and eventually accumulate as glaciers. During a very cold climate, we start to grow ice masses around the world. These are ice masses that are a couple miles thick. They get so thick that they deform under their own weight, right? And so they start flowing like ice sheets. That water was formerly in the ocean. Now it's no longer in the ocean. It's stuck up on land. And there's so much of it that it can cause a drop in the sea level around the globe. And we're talking about not just 10 feet, 20 feet, not 100 feet, not 200. We're talking probably at least 400 feet. 400 feet that sea level was lower during the last time we were cold, which is not that long ago, which is only about 20,000 years ago. The last time we were like this with this huge amount of ice on the continents was only about 20,000 years ago. During those really cold periods, sea level is low. When we're in a warm period like the present, sea levels are high because this ice melts and flows back into the ocean basins. So the sea level rises. That's what you hear about nowadays in the news. People are worried about the ice sheets in Antarctica, ice sheet or Greenland melting. That would take a while, but nonetheless, that's the idea there. So we can kind of look at this curve, and this is a temperature curve, and we don't have to discuss about how it was developed, but this is a history of Earth's history back the last 500,000 years. And the last time, here we are nowadays, right? And we're pretty warm here. Last time we were like this was about 125,000 years ago. And in fact, if you take a look at the numbers, it was even warmer. Sea level was higher about 125,000 years ago. If you were smart back then, you could invest it in property and bought waterfront property, right? So keep that in mind. That's one of the important controls. When it's warmer, we have higher sea levels. When it's cooler, we have lower sea levels. This is what the coastal bend looked like the last time it was warm, and it was warmer than at present. If you look in light gray here, those are that's the modern system, our modern barrier islands. Remember I mentioned Flower Bluff, the Encinal Peninsula, and Live Oak Peninsula, Rockport area? This was the last barrier island. This was a previous barrier island system. All these areas back here, the secondary bays that I talk about, were the Paleo Laguna system. Who knows Spanish? Do you know? So we've got Padre Island. Guess what this guy is called? Isla Abuelo. And we've got Laguna Madre. Guess what? Grandfather Island. And we've got Grandmother Lagoon, Laguna Abuela. So you guys here are sitting on an ancient barrier island. And it's not that long ago. Okay, in geologic history, it's very long from human time. But the point is, our climate system is heading towards a situation like this. So anyway, keep that in mind, because what's happening is all of our coastal features here, are really this equilibrium. They're in an equilibrium between the amount of sediment that's coming in, the amount of sediment that's being removed, all the processes that are working at in shaping the coastline. So it was only 20,000 years ago, that we were at the coldest period. We started up here 125,000 years ago, and we had this stair-step pattern, and about 20,000 years ago, we hit what we call the last glacial maximum, the last maximum part of the glaciation, last maximum part of the coldest period. This is when sea level was lowest. Sea level was 400 feet lower, at least. That would have dropped sea level all around the globe by about 100 or 120 meters, something like that. This is the Gulf of Mexico here, right? This, I have labeled 100 and 120 meter isobath. This is where, as soon as you're going out, you hit 100 meters or 120 meters depth. And so that was the shoreline. That was the shoreline not too long ago, only 20,000 years ago. This is what the continental shelf looked like. All this area here that's covered by water now, 300 to 400 feet of water, that was exposed. It was dry land. You can see this is some work done by John Anderson and his group up at Rice, and it's a compilation of some work they've done over the last, or not some, a lot of work they've done over the last couple of decades, and they put together this maps of what the paleo surface looked like, what that old land surface would look like. There were river systems, just like we see nowadays here, but they were flowing over the continental shelf. Not only that, this is what the area looked like. And we're talking only 13,000 years ago. There were woolly mammoths, giant ground sloths, saber-toothed cats, glyptodons, all those types of crazy Ice Age creatures that you see in those Pixar movies. They were here in South Texas. They were here in South Texas 13,000 years ago because it was a cooler area and the shoreline was way, 50 or 60 miles offshore. These animals were living here. You can go to, there's a part, this is from the Corpus Christi Geological Society, by the way. And in the past, I don't think it's happening anymore, but in the spring they would go to a gravel pit in Bloomsbury. It was an opportunity for kids to go out there, and the kids would pull out occasional, fossils once in a while, like a mastodon tooth or whatever. It's incredible. This was here in South Texas. In fact, if you go up to the Northwest Library branch in Corpus, it's been renamed the Owen Hopkins Library. There's like the front half of a mastodon sitting there that was excavated here locally in South Texas. So this was a completely different world not too long ago geologically. It seemed like a lot human lifespan, but geologically it's a very small amount. All right, this is super complicated. Don't worry about all the details on it. This is also from that John Anderson and his group there, okay? I'm gonna make it really simple. This is going back the last 12,000 years. And so 10,000 years ago, 8,000 years ago, 6,000 years ago, 4,000 years ago, 2,000 years ago, the present. And this is showing what the sea level was like over that period of time. So about 10,000 years ago, it was about minus 20 meters, about 60 feet below modern day. And then by about 8,000 years ago, it was about minus 12, so about 36 feet. And then by 4,000 years, it was about minus 4, so just 10 or 12 feet. The point is that sea level, it was really rapid once we were melting all that ice, and then it started to slow down, and it slowed down, and it became very gradual. And so we were dealing with real low, gentle sea level, rates of sea level rise on the order of 2 millimeters per year. Even in general, 0.6 millimeters per year. These are small amounts, stable amounts. Here's the kicker. Here are all the barrier islands along the Texas coast. From Bolivar Peninsula, Galveston, Follett, Matagorda, San Jose, Mustang, North Padre, South Padre. These lines show when they formed. These islands are only from the last 4,000 years, 5,000 years, maybe 6,000 years. This one's a little bit sketchy to me. It goes back so much further, Mustang Island. But the point is, all of these islands, when did they form? Did they form? I'm talking about the barrier islands. Did they form when sea level was skyrocketing up? No. They could only form when sea level had mellowed out, had slowed down, and then it hit this really relatively gradual rise. These islands formed during that period of time. Here's the preoccupation from a scientific point of view. All of those islands have been able to adjust. I showed you South Padre Island has migrated back 1,500 feet over the last 140 years or something like that. If we leave those islands alone, they've got no problem. They'll do what they need to do. They'll work with that process of rollover and they'll work themselves backwards, right? But they couldn't form during these periods of time. What happens is when sea level is rising too rapidly, all that vegetation doesn't have the possibility of adapting and migrating. This is the thing. This is sort of looking at the backside of some of these islands. You guys are aware there's very subtle relief there, not much, 10, 20, 30, 40 centimeters. And, you can have an area with nice marsh grass, and if you raise the sea level 10 centimeters and you give it time, the grass will migrate. It will start migrating backwards as the water expands. If you do it too fast, you'll drown the grass and it'll die. And so that's really what the concern is, because the sea level is now, I showed you it was like this the last 6,000 years, it's starting to do this. It's starting to go towards rates that we were seeing during the deglacial period. So it's a real concern. It's one of the big things that we're studying there at Hart Research Institute. Can these systems keep up with these changes in sea level rise? And goes back to some of those fundamental things that I talked about. Is there a specific, enough of a sediment supply? What about some of the other factors that I talked about as well? And the other point is, are we going to interfere and get in the way of these systems? Or are we going to let them do their thing? To do their thing, they have to migrate backwards. That's what they're doing. They're trying to maintain their equilibrium. They move towards the shoreline, or move towards the regular shoreline. It's very probable that places that have a really beautiful protective dune set on the front nowadays, like we see out on Mustang Island, that may start to trend towards those very, low dune systems, or a style that you see up like on the Matagorda Peninsula or South Padre Island. Because it's just, what's happening is the rate of sea level rise is picking up it's accelerating, right? It's getting much faster than is sort of stable for those, the island can bear.
What are the primary behaviors of man that exacerbate that?
Well, one of the primary behaviors is you buy a piece of waterfront property and you don't want to see, when you purchased it, the shoreline might have been 50 feet out or 100 feet out or something like that. But you want to maintain that.
So you put a bulkhead up.
You put a bulkhead up, right? And that's a temporary solution for sure, because eventually it'll be excavated underneath it, and if you put a bulkhead, great, but what about all your neighbors? So this is something that I guess we have to be thinking about, we're not going to be able to, I'm not trying to turn this into some type of catastrophe type thing, but as the sea level rises, we do probably have to pick certain select spots. You can't probably save every place. But certainly trying to maintain your waterfront property is a losing proposition. But I don't know how you tell somebody that after they paid a big chunk of money for it.
There's not residents on very large stretches of the area.
We're very lucky in this area, but other areas are just wall to wall. And if you look down at like South Padre, that's different as well. There's a lot of development right on the waterfront. It's kind of amazing that there's so little development here, which is wonderful.
So what time periods do you think this is going to occur during?
So we can make estimates and we can make our best guesses, but it's one of those things that it's like a forecast.
Yes.
You do your best guess and you can make an intelligent guess. Nowadays, people are talking about, we used to think 1 meter of sea level rise, or about 3 feet of sea level rise by 2100. Oh, that would be the extreme case. Now we're like thinking that's not the extreme case, and we could easily reach 2 meters. So that would make a difference if you're on Shoreline or Ocean Drive in Corpus Christi. You're not too worried about that because you're already 5, 6, 7 meters up. But if you're in any of the low areas, that's going to make a big difference. That's what we see, nuisance flooding more and more all over the place. It's not just a once in a 3 years or whatever. It's going to be every year and then multiple times each year. So just taking it back to San Jose to wrap up, we had those beautiful shorelines from 1860 or so, put together by the Coastal Survey, and the island is pretty much intact since that point. There's a couple spots over on the northern part, but here's one area where there's been some excellent evidence. There have been overwash, and that rollover process is happening. And it's great because really nobody's there in the sense like nobody's living there. But that's what the island needs to do to adjust and to keep up with it. So here's another example. This is the same part of the island there, but from the right after Harvey there. And we saw, this is previous to Harvey, and there's barges still out here in the channel as well. And you can see these breaches all over the place, and sand has been carried into the backside. Actually, sand also might have been coming out the front side too. It's a little bit crazy. When you look closely, you can start to see flow patterns that are actually this way, like parallel to the island. So that's still something that has to be studied. But the point is, if this island can adjust, hopefully it will. So I think that's it. I want to show you one more thing, and it's just to keep in mind. I want to show you a little movie from Cedar Bayou very quickly, because this goes to the point of, okay, well, let's try to make an adjustment and deal with it. The thing is that when we try to adjust the coastline, well, we go home at 5 o'clock, right? We work 9 to 5, maybe 5 days a week. Nature is working 24/7, 365 days a year. And so I'm going to show you this because it's so clear what's happening with this Longshore Transport, and especially the recent effort they made to open it. They opened it up, and within a short period of time, it's closed again because Mother Nature is never going to go to sleep. And this is just a compilation of satellite imagery since about the 70s. And I want to show you that every time this thing opens up, what happens? Longshore Transport keeps moving the mouth to the south, keeps moving to the mouth to the south, keeps moving the mouth to the south. Nature is never going to take a break. Nature is never going to take a break. And so we have to learn to live with nature in this sense. I mean, yeah, so the imagery is as bad as you go back in time, gets progressively better. And the cool thing about it is we start to see these, like I said, up to every 5 days or every 10 days, you can start to see imagery, provided there's no clouds. Every time it opens up, within a short period, it starts to close up and starts migrating to the south again. Well, anyway, that's what I wanted to tell you about today as far as that sort of geologic perspective on coastal change in Texas. We started to try to do some work with the folks at San Jose Island there, and with Chuck's been asking for some imagery. We can show him some of the areas, how these have changed through time. And so this is a project in progress pretty much, and something that we'll keep working on.
So sea level rise, you showed there's a cycle to it that comes and it goes.
Yes, sir.
And there's clearly an effect from man's
contributions.
So in the professional opinion, though, prevailing professional opinion, what is the biggest component? Is it more of a natural cycle we're seeing in the sea level rise, or is it?
Oh, it's pretty clear. I mean, I read a lot about it. I'm still not a top expert about this by any means. And so there are people that have dedicated their life to it. There's no question about it. We can put together computer models. A computer model is not real life, okay? But it gives you an approximation of how a system can work. And we can show that this rise, and it's related to CO2 in the atmosphere. I didn't want to go get anybody crazy about this, but here, maybe I still have it in one of my slides. I don't want to be alarmist, but I just want you to realize, right? I showed you this curve. This is basically the temperature on the planet, warmer as you go higher, cooler as you go lower. This is a record of CO2 on the planet. And we get this, part of it goes back with the work that they were doing at Mauna Loa. They have back to the late 50s, the Keeling Curve. They go out there and they sample, take a sample of the atmosphere every point in it, and then they measure how much CO2 is in it, right? And so that's since the late 50s, but then we could take that further back in time. One of the geologic tools and techniques that I told you about is I take sediment cores. Other people take ice cores. They can go take ice cores from Antarctica, Greenland, the Arctic, things like that, higher altitude areas. And as we talked about, as snow settles down there and it starts to compress on itself, right? Well, there's little air bubbles in between there, and you save air bubbles in those ice. And if you do it the right way, you can crush up that ice and extract the air. It's like an air sample from 10,000, 15, 100,000, 400,000. We can go 800,000 years now. 800,000 years of Earth history, we know what the CO2 was like. And even at the peak of these warm periods and the cold periods, it's always been between 180 and 280 parts per million. Over the last 800,000 years. Even the warmest period, it's only made it up to whatever, some areas might have made it up to 300 million. Do you know where we are nowadays? We crossed 415 parts per million. This is in the last 150 years we've done that. It's okay. It's not bad. I mean, I like going home. I was happy I could put gas in my car and come here. I like going home, turning the lights on. I want to use energy, but it's just, as well. So I'm not saying that we have to do that, but we have to think about how we're using it. The other thing is, people say, oh, how can we possibly do that? Well, what's happened is that the Earth is our spaceship, and we've got the atmosphere above us. That's only maybe 7-10 miles thick. And so what we've done is, a lot of that carbon that was stored over geologic time, over tens of millions, hundreds of millions of years, we're just very good at extracting it from the ground, and we threw it back into the atmosphere. So when you think about how thin the atmosphere is with respect to the whole planet, it's something that we can certainly change the volume. There's no question that we're altering the composition of the atmosphere.
Going back to that gentleman's question, is the consensus now that maybe is 60%, 80% of what we're seeing in CO2 change, the change over time, that we attribute to man? What is the general professional?
For sure. So there's different contributions. There's different contributions to what, for example, burning fossil fuels. There's also things that are not necessarily directly fossil fuel burning, but they're a function of it. Because, for example, if we go up to the high Arctic, where there's lots of permafrost and lots of buried frozen soil, right? That is basically, it's been in an ice box for hundreds of thousands of years now. If we're warming it up to the point that that material can start to decay, be broken down by bacterial composition and produce CO2, that's sort of a feedback. So I don't know the exact number, but for sure that trend upward is by contributions that we've made. I don't want to get into too much, I'm not trying to be alarmist or anything here, just trying to be definitely straightforward. It's something that we're doing.
But we're affecting everything. I mean, you were talking about the sediment coming out of the rivers. We put dams and flood control on every river in the world.
Yeah.
And all the river deltas, they complain because they're not getting the sediment they need, but we're not dumping the sediment into the Gulf for it to even come here.
Well, that's right. I mean, we don't have to look any further than the Nueces River, right? We've got a couple waterworks upstream of that, and it is clear as a bell that something happened, because we can use those old maps that I told you about, and then aerial photos, early air photos. We could see that Nueces Delta is doing fine. It's actually prograding. It's actually growing into Nueces Bay. And then in the 70s or 80s, I'm not quite sure, it kind of hovers, and then it starts moving backwards. we trapped all the sediment. It doesn't get sediment anymore. And so people might look at that and say, it's a mosquito breeder, who cares about that marsh? But I think something like 90% of all, and don't quote me on this number, somebody will know better than I, I'm not like an ecologist, but it's a very high number, 90% or so of all marketable or sport fish, shellfish, something like that, spends one life stage in these areas, in these wetlands. And so, I mean, there are going to be cascading effects down the road because of this. So, other thoughts? I'd be fascinated to hear about some of the, Native American archaeology and things around here. And I saw back there the case of arrow points and things like that. So I brought a poster of the South Texas Ice Age if you want to take a look at that as well.
I don't know how to word this, but over that millennium of time, however much that is, what natural effects were involved in the rising and lowering of the CO2 levels?
Okay, so
Today and then what in the past history?
okay, so
Just next.
okay, so for example, we have the biota, right? And in fact, that's something that we can even see on a yearly cycle. It's so fascinating if you ever go take a look at the CO2 curve that they're getting off of Mauna Loa, because you see a peak in a valley and a peak in a valley every year, and that's related to the fact that our land is asymmetrically distributed. We have much more land mass in the northern hemisphere, about 70% of it, than in the southern hemisphere. And when the northern hemisphere wakes up for the spring and the summer, and those plants wake up and they suck the CO2 down. So that's what brings it down. And then during the fall and the winter, when that biota dies off, it goes back up. So that's one thing. Another place that where a lot of the CO2 is going is into the ocean. And so this is another thing that people talk about. It's one of those things that you don't see it, so you don't think about it. If CO2 was green and we saw our atmosphere getting progressively greener, you'd see people say, well, what's happening? But it's going into the ocean water. And some basic chemistry, when you mix water and you mix CO2 together, you form a weak acid called carbonic acid. And then it makes it much harder for all of those marine organisms to calcify, to make their shells. So things like coral reefs or the phytoplankton that are the base of the food chain that feed the next bigger organism, that eventually feed the fish that we are happy to catch and stuff. They're all part of that trophic cascade there. So that's another area where we're putting a lot of this CO2 into the ocean. And the thing is that has a lot slower cycle time. We're on the order of, 1,000 years or more. So it's like a down payment we're putting on.
Is there a significant change of atmosphere, low atmosphere, between the southern hemisphere and the northern hemisphere?
Good question, because maybe things are sort of segregated. No, there's a lot of studies that show that mixing is very fast. And so the changes that we see in one hemisphere quickly are propagated, within a year to the upper one. So the atmosphere is very well mixed. So I don't want to turn this into an environmental alarmist thing at all. This was about history and stuff, showing you how that we worked backwards in the past. Well, I mean, we've got these beautiful features here, and then it is a little bit makes us nervous to think that if sea level starts rising faster and faster and faster, are they going to be able to keep up?
What time to sail?
So we're not talking about anything imminent the next 3-5 years, but it's one of those things that.
I don't think I have any problem.
Go ahead.
When you talk about the rates that the barrier islands migrate, when we graph it and things, it looks like it's fairly smooth. Mm-hmm. A lot of it has to be in sudden events.
A lot, for sure.
I looked at a similar map where they showed Mustang Island and Corpus Christi Bay, and Corpus Christi Bay, Oso Bay, all the far bluff shoreline exactly matches today. Mm-hmm. And Mustang Island, about where Factory Channel is, was exactly the same shape, but it was 3/4 of a mile further out. Uh-huh. And the coastline then was about where the end of Bob Hall Pier is now.
So fair enough, and that's an area down by Bob Hall Pier where they are seem to be significant erosion. We put together the best history we can. For certain, the more information that we have, the better. But the big rates that I was talking about, and I mean, those are produced by the Bureau of Economic Geology, not me. Those are pretty good estimates based on, and there's a lot of imagery, like aerial imagery going back to the 30s with those things. So,
but we tend to think of it as smooth motion when a lot of it probably happens with 10-year, 20-year storms. And we see new passes cut through the islands, and then as the passes fill in, it's just changed a little bit. So.
Yeah, so fair enough. There's probably some hydraulic changes that make a difference as well. For example, with the Aransas Pass jetty, we opened that up, and that's a really good conduit, right? And so then we have all these old, we have these hurricane overwash passes like the 1851 Pass, Newport Pass, Corpus Christi Pass. Those things open up not infrequently, but it seems like they're opening up less and less, and that might be because there's more through flow through the the Aransas Pass system there.
Or they're coming in faster once the storm.
Yep, that's right. It's not vigorous. The flow coming through them is not vigorous enough. And we've got pictures. I take my class out all the time to Newport Pass, and we take sediment cores there. You go back to the 50s, and it's like it's all water, and then it's filled in very quickly. So those overwash channels are important for bringing the sediment from the front side of the island to the back side of the island. But they do tend to fill in pretty quickly. And I'll come to you. Go ahead.
Do you know if the state ever removed the structures there at Rollover Pass at Galveston? And if so, what happened after that took place?
Could you say that one more time? I missed the first part.
Do you know if the state ever removed the structures there at Rollover Pass? They was bulkheaded and they were, I was taught last time I heard this several years ago. They were,
I don't know myself personally.
Tied up in lawsuits, I don't know.
Yeah, I don't know personally, but we could certainly get you an answer on that.
Oh, I'm just curious.
Is there any concern or reason to be concerned about the additional dredging of Aransas Pass across the channel?
Well,
to open up more water coming?
So the good part about that is people are trying to think about these things intelligently nowadays, right? And so we have this whole concept of beneficial use of dredge material. And so instead of just dredging that out, it's actually, it's to put that material in some place that could help it be more effective, keep up with sea level rise or whatever. So there's good things that can come out of it as well. So it's maybe thinking, in the past, we didn't think too many steps ahead. Now, if we can think a step or two ahead, we can help ourselves out somehow. For example, with that dredge material, do something useful with it.
But the hydraulics?
By picking up the flow, I don't know many details about that. It's not something that I study. But certainly that would be, but by cleaning out the channel, it's going to, it's going to increase the flow through it. And that might even more.
The argument was that if you increase the flow at these passes like that, the hydraulic punch of a place like Cedar Bayou loses some of its oomph. So it seals in more. So that and the ICW as well subtracts some of that flow.
And all of the water, maybe there used to be tremendous flooding. A lot of that's trapped now just because of these waterworks. And so we don't have that same flushing that, so I don't have an answer for that because all of those waterworks are critically important as well.
We're not going to undo them all, so yeah, it's not going to happen.
Right.
Tell me, has anyone pointed out the irony that Greg Stuns is studying the benefits of an open Cedar Bayou with one research, and then down the hall you're saying it's not worth it? Well,
no. I mean, what they point out, and it's true.
Right.
There's no question about it. If that stays open, then there's recruitment, there's larvae and stuff that move through that, and they can get into the back there much more easily than making the trip down and then back up.
You're probably paid by the people who wanted to open it, and they wouldn't pay you.
No. Here's the thing: if there was a way to keep that thing open naturally, it would be a benefit. But I just don't think.
Proving the benefits.
Yeah, the benefits are proven, but it just.
At $10 million a pop.
Well, that's what it is. I mean, it's like you put your finger in the dike, you can never let it out. Any other thoughts or questions? I would invite you all to come and visit Hart Research Institute. So I'm part of the CMGL, the Coastal and Marine Geospatial Lab, but it's a fantastic place doing just a ton of great science, and that could be of interest to you. I know this is the more history focused and stuff, but all of those guys would be thrilled to have these long-term histories that we could get like as geologists, so all those the anecdotal comments by a fisherman or something, a clipping in a newspaper or comments in a historical document, those are probably quite valuable, so to help understand the system. So okay.